SDM 2.0 support file, narrated by Susan Arnold. The learning objectives for this module are to demonstrate how to use the Structured Deterministic Model 2.0 support file. If you executed a license for the SDM 2.0 tool and downloaded the two files, you'll already have the support file. If not, complete the license application process located here. You'll need to register for an account, after which you'll be sent a link to download the SDM 2.0 tool and the SDM 2.0 support file. The SDM 2.0 support file includes useful information about the Structured Deterministic Model, or SDM 2.0, including information that is helpful for applying the SDM 2.0 to real-world scenarios, spreadsheets for useful calculations and conversions, background information behind all the algorithms implemented in the software, and case studies illustrating the application of the algorithms to real-world scenarios. Clicking on the arrows beside a given text box takes the user to the page related to that topic. The support file is evolving and will be updated periodically with new information. Vapor pressure is a critical input for two algorithms used in the SDM 2.0 tool. The rule of 10 and vapor hazard ratio algorithms predict the airborne concentration of chemicals based on evaporation. The propensity of a chemical to evaporate is heavily influenced by its vapor pressure, and vapor pressure is temperature dependent. For many chemicals, published values for vapor pressure at non-ambient temperatures are not readily available. The support file includes two methods for estimating vapor pressure across a range of temperatures: the Clausius-Clapeyron equation and the Antoine equation. Briefly, the Clausius-Clapeyron equation can be used to estimate the vapor pressure at non-ambient temperatures if the vapor pressure at 25 degrees C is known and at the boiling point, representing the temperature at 760 millimeters of mercury. The calculator will provide an estimate of the vapor pressure at the temperature of interest between the 25 degrees and boiling point range. Inputting more temperature vapor pressure values will increase confidence in this value, but two inputs can be used to estimate the vapor pressure. To change the temperature on the calculator, the user toggles the up or down arrow located on the left of the temperature value. To illustrate why it is so important to use the vapor pressure at the relevant surface temperature of the chemical, watch how the vapor pressure changes in this demonstration as the temperature increases. Notice that the vapor pressure nearly doubled when the temperature was increased by 10 degrees. The unit converter page includes several useful conversion calculators. For the SDM 2.0, vapor pressure and temperature converters, shown in the lower third of this page, are the most relevant. On the concentration converter page, the user can convert from parts per million to milligrams per cubic meter and vice versa. This can be done for both normal temperature and pressures and non-ambient conditions. From the Guide tab, the user can learn more about the algorithms that produce the exposure estimates in the SDM 2.0 tool by clicking on the arrow beside the specific topic listed in the text box. The rule of 10 is also defined on the rule of 10 page. This concise reference page describes the basis and application of the rule of 10 and gives several examples for each level of control. The paper describing its evaluation and performance on improving exposure judgment accuracy is listed on the bottom left of the page, along with other useful references. More information can also be found in the AIHA publication, A Strategy for Assessing and Managing Occupational Exposures, 4th edition, referenced on the home page of the tool. Similarly, the vapor hazard ratio, another major algorithm included in Checklist 1 and introduced in the SDM 2.0 module, is summarized here. Like the Rule of 10 page, examples are provided to further demonstrate how this algorithm can be used in real-world scenarios. Its application is further described on the controlling compound page. The controlling compound provides a scientific basis for prioritizing specific components of chemical mixtures for the efficient evaluation of the individual components as well as the mixture overall. The application of the controlling compound to real-world scenarios is concisely described here. Rayle's law and its application to chemical mixtures is introduced on the Rayle's law page, shown here. It provides a summary of the theory and the specific equation. The guide page for Henry's law provides an explanation of the theory of Henry's law and how it is applied to estimate vapor pressure in the SDM 2.0. The premise for estimating airborne concentration through evaporation is the same as with Rayle's law. The gray box on the top left, labeled Henry's law calculation, will take the user to the still under construction Henry's law estimator. The vapor hazard ratio and rule of 10 scales are linked to different levels of control. Accurately identifying the types of engineering control is critical. This tab is grayed out to indicate it is not yet active. In the near future, it will take you to a more detailed definition of the types of controls listed in the Observe Levels of Control drop-down menu found on the SDM 2.0 tool, with images or drawings to guide the user. For chemical mixtures, the same algorithms that apply to pure chemicals apply to mixtures, but a few extra calculations are required. The Mixtures Calculation tab provides a concise explanation of how the various mixtures-related parameters are calculated and serves as guidance for scenarios that might need a little extra detail in how to proceed. The Expanded Health Risk Ranking tool page describes how it can be applied to drive decisions, activities, and communication efforts. The information and guidance contained here, including a consideration of frequency and duration, provide a rational basis for prioritizing those activities and communication efforts. Valuable additional contextual information for the different OELs can be seen by clicking on the Agency OEL link. On the OSHA page, for example, the user can see which chemicals in the SDM 2.0 database have OSHA PELs, the type and value of the PEL, and the maximum duration of exposure permitted. On the REL page, the user can see which chemicals in the SDM 2.0 database have NIOSH RELs, the type and value of the RELs, target organs, exposure routes, and synonyms. There is also a link to the NIOSH Pocket Guide page for each chemical. ACGIH values and basis for the TLVs are copyrighted materials. They can be accessed through the Data Hub link. The links at the top of this page will take the user to the YouTube videos and general information about ACGIH TLVs. Using the drop-down menu, the user can select a specific chemical to search on the Data Hub site. After selecting the chemical of interest, the user clicks on the ACGIH TLV, and provided there is internet access, it will connect to the chemical-specific ACGIH TLV page. On the Wheels page, in addition to the value and type of wheel for a given chemical, likely routes of exposure are indicated. Acute Exposure Guideline Values, or AGLs, set by the US EPA are rather unique in that values may be listed in units of either ppm or milligrams per cubic meter. If you use these OELs, be sure to check and report on the units. At this time, only 2 of the admin help tabs are active, the one describing running macros and computer requirements, and a link to provide comments on the tool. These will go to Daniel Drolet, the developer of the SDM 2.0. This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.